Hi everyone, it's Wednesday, which means it's time for another Chem Help ASAP live stream. So tonight we're working on equilibrium. However, I do want to make sure that I tend to say this at the end, but I want to say at the beginning too. Please let me know what topics you would like to see. If you've got either a topic that's confusing you in class, or even if you have a specific problem. Hey, my teacher did this problem or gave us this problem for homework and I just don't know how to do it. You can send me suggestions for topics, but also specific problems you want to work. I'm happy to work those problems and to explain kind of what's going on with that. So what my hope is with the live streams is that I can help as many students as I possibly can work through their chemistry class and just understand it a little better and maybe be a little more comfortable in class. So with that being said, tonight we're going to talk about equilibrium. So we have talked a little bit about equilibrium when we did weak acids and bases. So we have used equilibrium, but I thought it might be good to talk about just equilibrium on its own. What it is, what is K, how do you calculate K, how do you use that to calculate concentrations, what is Q, how do you determine which way an equilibrium is going to shift. So these are all the things that I hope to get to tonight. But of course, I welcome any questions in the comments. So if you've got a question, just pop it in the comments and I'll try to catch it. I mean, I keep looking over here to make sure there are comments. I see my audio is low. So if I don't see your comment right away, just give me a minute and I'll catch it. So OG benchmarks, hopefully that audio is a little bit better. I did bump it up a bit. Okay, so let's get started. All right, so equilibrium. This is just, again, I like to start with definitions. Where are we? How do things work? Let's lay a little foundation first before we jump straight into calculations. All right, so equilibrium is a dynamic state. So it is dynamic, meaning things are happening. It's not static, but it's where the concentration of all species remains constant. So there are two plots that I want to draw for you. Okay, so bear with me because drawing plots is not necessarily my strong suit, but I'm going to do my best. All right, so we'll start with plot A here. And we've got time on the x-axis and equilibrium is kind of moving forward here. We have concentration of species on the y-axis. And what you're going to see is products, your concentration of products is going to start at 0. It's going to increase, and then it's going to level off. Oh, I should have done that in a different color. My bad. I'll do reactants in a different color. Reactants are going to start at a specific concentration. They're going to come down, and they're going to level off. Okay, so blue is reactants, and black is products. So often with these graphs, the classic question is, where has equilibrium been established? Well, we know it's where the concentrations of the species remain constant. So what you want to do is you want to find the point on this graph. Let me get that out of the way. Find the point on the graph where both of those lines for products and reactants are straight. And so they're not either curving up or curving down anymore. And the way I've drawn this, I would say that was about right here. Now, again, my drawings are not the best, but that is where I would say I attempted to go straight with my lines. So equilibrium is established right here. I'll write this up here. So equilibrium established. So the other thing I want to point out about this plot is you'll notice that the concentrations are constant, but they are not the same. So the concentration of the reactants does not equal the concentration of the products. It's just that they're not changing anymore. They are constant. However, it's a dynamic state. So there's always a forward and reverse reaction happening. But, and this is my next plot, the forward and reverse rate are coming together. They are then the same. So let me draw that plot. So this is the other condition that must be met for equilibrium. So we have a state where the concentrations, again, it's a dynamic state. It's not a static state, a dynamic state where the concentrations of the species are constant. But if I draw my second plot here, and this time, this is still time. This over here is reaction rate. This time I am going to change colors properly. All right, so we have, we'll start with our reverse reaction. Our reverse reaction rate initially is 0 because there is no reverse reaction, but then it builds, right? Okay, and then you've got your forward rate, which starts high because initially you only have the forward rate, and it comes down and it meets the reaction rate of the reverse. Okay, so this is forward rate, and the blue is reverse rate. So this is the rate that the forward reaction is happening, and this is the rate that the reverse reaction is happening. And they do, at equilibrium, they are equal. So if I'm going to mark my equilibrium spot, it's going to be where these two lines first come together. So here we have equilibrium established. And this is what makes it dynamic. So one thing I think about is if you have like a 2-story building, you have people going up the stairs and people going down the stairs. But if the rate of people going up the stairs and down the stairs is the same, then you will in essence keep the number of people downstairs and the number of people upstairs constant. Now they might be different. So maybe you have 100 people always downstairs and 80 people upstairs. But as long as for every one person that comes downstairs, another person goes upstairs, you're going to keep the same number of people upstairs and downstairs. So the rates are the same. The concentrations are constant, but it is still a dynamic state. So again, people are still moving up and down the stairs, but they're just moving at the same rate. Okay, so that is what equilibrium is. This is how experimentally we find when equilibrium has been established. So now we're going to start moving into the equilibrium expression and K and how we write K and then how we do our calculations. So K is a constant and it is an equilibrium constant. Now sometimes you will see K as written as KEQ as the equilibrium constant. You also might see it as Kc. This is the equilibrium constant for concentrations, or Kp. This is the equilibrium constant if you're measuring pressures there. Anyway, there are several of them there. We've also seen Ka. That's the equilibrium constant for an acid. But let's just generally see how we write a K for an equilibrium expression. Okay, so all of these reactions are in equilibrium. So you'll see all of my reactions are going to have the double arrow. Now, okay, there is something that's a little bit of a pet peeve of mine that I just have to mention. This arrow right here is not an equilibrium arrow. That is a resonance structure arrow. Your equilibrium, it has two separate arrows, one on top of the other. Okay, that is not equilibrium. I'm going to draw a big red X through that, okay? So that is resonance arrows. Those are not equilibrium arrows. I think OG benchmarks will agree with me on that as well. Okay, so let's go back to, actually I want to make this a little thicker. Let's go back to writing K. So when we write K, it's going, and we'll do concentrate, we'll do KC for all of these, in essence concentration. It's going to be the concentration of the products over the reactants. And the trick here is you are raised to the stoichiometric coefficients. So if I am writing K for this reaction right here, my products are capital C and capital D. So capital C and capital D, but they are each raised to their stoichiometric coefficients. So capital C is raised to the little c, and capital D is raised to the little d, and that's products, and we put this over reactants. So this is going to be capital A raised to the little a, and capital B raised to the little b. So that is how we write all equilibrium constants. Now you don't have to have two reactants and two products. You'll see we're going to work with reactions that have two reactants and one product, or one reactant and two products, or you could have three reactants and one products. But the formula is still the same. You're going to take the concentration of your species and you're going to raise it to its stoichiometric coefficient, which is also why it's always important to start with a balanced chemical equation. Okay, let's make sure there are no questions. Yeah, OG benchmarks, I knew you'd agree with me about that resonance arrow. Okay, so let's practice writing K for some actual reactions. So we kind of did the general reaction, but let's write it for these reactions. Okay, so I'm going to start with this top one right here. Now these reactions are already balanced, so woohoo for that. So my K for that reaction, I'll make sure I'm not writing over my face. Okay. Is again, concentration of products. So my concentration of nitrogen monoxide, that is going to be squared because it has a coefficient of 2 in front of it. And then my concentration of chlorine. Now that is raised to the 1 power because again, there's nothing written here, which means we assume there's a 1. And again, I can write the 1 there, but generally we don't write 1s. So I'm just going to leave it alone. And then that's products over reactants. So this is NOCl. And this is also squared because there is a 2 right here. Okay, so that is K for our first reaction. So let's do our second reaction right here. So same deal here. Products. We've got hydrogen gas. Again, it's raised to the first power. We've got carbon dioxide. It's also raised to the first power, and this is going to be over water vapor raised to the first power and carbon monoxide raised to the first power. So sometimes you'll have a KEQ like this where nothing is raised to the power. You can think of it as everything is raised to the first power. So you just have to make sure you're starting with a balanced chemical equation to make sure you know what power to raise each of your species to. I hear my cat meowing. All right, so the other thing I want to put in here is just a little discussion on heterogeneous equilibrium. So you'll notice these first two reactions here, all of my species were in the gaseous state. So how do we handle when we've got solids? What's going on with that? Well, let's start with this calcium carbonate one right here. And I'm just going to write everything in. So again, it'd be products, carbon dioxide. Those are both raised to the 1, and over calcium carbonate, also raised to the 1. So when you have a pure solid in this case, or a pure liquid, then these quantities, let's see, this is going to be this one, they go to 1. and the calcium oxide, it goes to 1. So it doesn't go to 0 because then we'd be divided by 0. So it doesn't go to 0, but it goes to 1. And this ties into something called the activity of the substance, and it has to do with the reference substance. I'm not going to get into what activity is. I think most classes just say pure solids, pure liquids, just go ahead and ignore it. So this simplifies the K for my first reaction right here. It's just dependent on the concentration of carbon dioxide. So a lot of times these heterogeneous equilibrium, the equation can look complex, but then when you pull out your pure solids and your pure liquids, then it looks a lot simpler. So let's do the same thing for my second example right here. So again, it's going to be products over reactants. And let me get my reactant in. And now I'm going to pull out my pure solids and liquids. So in this case, that is going to be this one. That goes to 1, and those two gases stay in. So this equation simplifies. It's still a fraction or a ratio, but it has simplified. Okay, so that is how you handle heterogeneous equilibrium if you've got a mixture of gases, solids, and liquids. All right, any questions? All right, does it look like there are any questions? So we are going to move on to the next page. Now we're going to get into our calculations. Okay, so we need to calculate K for this reaction at 315. Now, most of the times when you're calculating K or using K, they will give you a temperature. This is because the value of K changes with changing temperature. And we'll talk about how to predict those shifts a little bit later when we talk about Le Chatelier's principle. But this is why when you have these problems, it will specify a specific temperature, and it'll say things like the temperature is held constant. So because K does change with changing temperature, but we don't actually have to use this number for anything. It's just this is the K at this temperature. Okay. So let's actually calculate what K is. To calculate what K is, we have to first write down what K is. So back to our practicing our equilibrium expressions. So that is squared. This is to the first power. And of course, like we saw before, this is also squared. All right, so remember, when I'm using these brackets, I'm talking about concentrations, and specifically I'm talking about usually molarity. Sometimes you'll see molality, but almost always these are going to be concentrations measured in molarity or moles per liters of solution. Okay, the nice thing is for this one, it's a fairly simple one because I have values for all of these concentrations. So I am simply going to plug the value into K that the problem gave me. So this is equal to, so my nitrogen monoxide is right here. So this is 4.8 times 10 to the negative 3, and that is squared. My chlorine is right here at 1.7 times 10 to the negative 2nd, and that is just to the first. And over my product, that is going to be 3.5 times 10 to the negative 2nd, and this is also squared. Now, K is unitless. Actually, the units do work out, but it's just easier to say K is unitless. So you notice I don't put my molarities in. I'm not going to call this, this would end up being just molarity, but we're just going to keep it unitless. Now, I did this calculation, and I got K to be 3.2 times 10 to the negative 4th. So this is the value of K for this reaction at this specific temperature. Okay. Let's talk about part B. So part B says calculate the value of K for the reaction again at 315, but this time they didn't give us any concentration. So how are we supposed to calculate K? Well, there's something that you might notice about this reaction. This reaction is just this one written backwards. So what happens when we do that? Well, we flip our reactants and products. So our K new, we'll say, is equal to 1 over our K old. So that is our K up here. So all you need to do is just take the inverse. So what I'm going to do is just take the inverse of 3.2 times 10 to the negative 4th. And that gives me 3.1 times 10 to the third. So for these, if, this is handy if like you're looking up K's and you can find the K for the reverse reaction that you want, just take the inverse and that'll give you the K of the reaction that you want. So this is a really handy trick if you need to calculate a K and you don't have the exact reaction, but as long as you have the reverse reaction, you're totally good. So there's another trick that I also want to show you. So if you look at this reaction right here, again, we're supposed to be calculating K. This reaction is just about the same as this reaction, except I have multiplied through by 2. So this reaction is multiplied. The stoichiometric coefficients are multiplied by 2. So that means this time my K new is equal to my K old squared. So you just raise it to whatever power you've multiplied through by. So this is going to give me 3.2 times 10 to the negative fourth squared, which gives me 1.0 times 10 to the negative 7. So these are just kind of handy rules to have ready and available. It's also a very common twist that teachers or professors will put on a test. They won't give you the exact K you need, but they'll give you the K of the reverse reaction, or they'll give you the K of a reaction that's been multiplied through by 2 or by 3. Well, this is how you get to the K that you actually need. Okay, so it doesn't look like there are any questions, so let's keep going. Let's talk about Le Chatelier's principle. Okay, so I have summarized Le Chatelier's principle in these steps, but I'll also write reactions and kind of show you what's going on. So in a nutshell, Le Chatelier's principle states that any stress applied to a system at equilibrium, so first you have to establish equilibrium, then you apply some kind of stressor, it's going to cause the equilibrium to shift in the direction that reduces the stress. Now you say, reduces the stress, what does that even mean? Well, it means different things for different types of stressors. So I want to talk about 3 main types of stressors that we put on systems at equilibrium, and then how the equilibrium changes because of that. Okay, so the first one here are changes in amount, and sometimes you'll see this as changes in concentration, but it doesn't necessarily have to be concentration. It can be a change in amount that's a change in pressure, or it can be a change in amount that is like precipitating out a solid. So this is just a change in amount. So if you increase the concentration, it's going to shift the equilibrium away from the increase. So let's get an example in here, and we'll use the classic example of nitrogen and hydrogen in equilibrium with ammonia. But we can't leave it like that. We do have to always balance, right? 2, 3. Okay, so we're balanced. So for example, if I were to increase my concentration of nitrogen, my equilibrium would shift to the right. It's going to shift away from the nitrogen, shifting away from the stress. If I am going to increase my concentration of ammonia, I'm going to shift away, so I'm going to be shifting left. So this is why I don't specifically say shift left or right, but I'm saying shift away from the increase. Because if you increase the reactants, it's going to shift away from the reactants towards the products. If you increase the products, it's going to shift away from the products towards the reactants. So anytime you increase an amount, you're going to shift the equilibrium away from wherever you've made that increase. So the opposite is true about decrease. So if you decrease your concentration or you decrease your amount, the equilibrium is going to shift towards the decrease. So if I decrease my amount of nitrogen, let's say I'm removing nitrogen as the process goes, then I'm going to shift towards the nitrogen. So the reaction is going to make more nitrogen. The same is true for the ammonia. If I am pulling ammonia out of this reaction, then the equilibrium is going to shift to make more ammonia. It's going to shift towards that decrease in amount. Okay, so that is amount. Let's talk about changes in pressure, and this actually ties more to changes in volume. So changing your volume is a great way to change pressure, but there's also another way to change pressure too, which we'll talk about at the end. Okay, so Let's say you decrease the volume. So you've got a rigid container, maybe you've got a piston or something similar, and you decrease the volume. Well, when you decrease volume, remember volume and pressure are inversely related. When you decrease volume, you are going to increase the pressure. So which way is the equilibrium shift? Well, this depends on the reaction. It's going to shift the equilibrium to the side with the fewest moles. So the way I think about this is, if you decrease the volume, then the reaction is going to try to make itself as small as possible. So that's why it's going to shift to the side with the fewest number of moles. The next question probably out of your mouth is, how do you know how many moles you have? Well, let's go back to our ammonia example right here. So all you're going to do to figure out how many moles you have on each side is you're just adding the stoichiometric coefficients. So for my reactant side, I have 1 plus 3. Again, we assume there's a 1 in front of the nitrogen. So we have 4 moles on the reactant side. And my ammonia is just by itself, so there are 2 moles on this side. So if I decrease the volume of this reaction, again, it's going to shift to the side with the fewest number of moles. It's going to make itself as small as possible. So that is going to shift it to the product side. Now, the exception to this is if the moles are equal. So if you get the same number of moles on both sides, then there's no shift in equilibrium at all. So in that case, decreasing the volume doesn't shift the equilibrium. But in this case, because I have a different number of moles on reactants and products, if I decrease the volume, I'm going to shift to the products. Okay, so now what happens if we increase the volume? Well, the reverse is going to happen. So if you increase volume, we are going to decrease pressure, and the equilibrium is going to shift to the side with the most number of moles. So in this case, if I increase the volume, which decreases the pressure, my reaction is going to shift to the reactant side because it's the largest. It's got 4 number of moles. It has 4 moles. Again, if moles are equal, there is no shift in equilibrium. So when I think about these changes in pressures, changes in volume, which does change the pressure, I think about, does the reaction want to make itself bigger and take up more space, or does the reaction want to make itself smaller and take up less space? Now, the third way that we can change the pressure is we can add an inert gas, but this does not cause any shift. Again, this is a classic trap to fall into, especially in a multiple choice question on a test, is they'll talk about changing the pressure, and then they'll talk about, okay, well, you've increased pressure by adding argon or helium or some other inert gas. Well, you immediately go to, increased pressure, and you would think that you're going to shift to the side with the fewest number of moles. But no, remember, if you're adding an inert gas, it does increase pressure, but it's going to cause no shift at all. Okay, so that's just a little trick to watch out for. Okay, so number 3 in Le Chatelier's principle, changes in temperature. See, I told you we'd come back to changes in temperature. Okay, so when you change the temperature, you will change the value of K. So let's talk about an endothermic reaction versus an exothermic reaction. So let's just get a general reaction here. Let's say A plus B goes to C. If it's exothermic, then I'm going to write energy as a product. Okay, because an exothermic reaction produces energy. So I think this makes more sense if you think of energy then as a product for exothermic reactions, because it ties back into changing the amount. So exothermic reactions, if you add energy, it's going to shift the equilibrium left. So think about this. If you think about energy as a product, if you add energy, if you increase the temperature and you're adding energy, you're going to shift. Oh my goodness, I can't believe I did that. You're going to shift away. I didn't put in my equilibrium arrows. I'm sorry. You're going to shift away from that added energy. So you're going to shift to the left, you're going to shift to the reactants. So if you think about removing energy, so you decrease this amount of energy, you're going to shift towards it. So you're going to shift to the right, you're going to shift to the products. So I like thinking about the temperature changes as having energy as either a product or reactant, because then I'm using the same rules that I use for changing the amount of either a reactant or a product. So let's write a general equation for an endothermic reaction. So why don't we say A plus energy goes to, I don't know, B plus C. Why not? Okay, so this is an endothermic reaction. You need to put energy into the system to make it go, or you can think of it as absorbing energy, either way. So if we add energy, then we're adding a reactant. So we're going to shift away from that. We're going to shift to the right. Again, if we are removing energy, if we are removing a reactant, then we're going to shift towards that removal. So we're going to shift left. So this is how you handle Le Chatelier's principle in terms of changes in amount or changes in concentration, changes in pressure, which correlate with changes in volume, and also changes in temperature, which is really changes in energy of the system. Okay, make sure there are no questions. All right, no questions. So let's just keep on trucking here. So now we're going to get into, again, some more calculations. And we're going to start calculating Q. All right. So we've got Le Chatelier's principle, so we can know if something's going to shift left or it's going to shift right. But how do we necessarily know if we're just given numbers? So sometimes it's obvious, like if you have no product, well, your equilibrium is going to shift to make product. But what if you have some product, but not a lot of product? Well, you're going to use Q to predict your equilibrium shifts. Now we write Q the exact same way that we write K. So Q is also products over reactants, and they're all raised to their stoichiometric coefficients. Okay, but here are kind of the conditions that we need. If Q equals K, then the system's at equilibrium. If Q is greater than K, the equilibrium is going to shift left, or it's going to shift towards the reactants. If Q is less than K, you're going to shift right, or you're going to shift towards the product. So for this problem here, we know, so given the following reaction, so we're given K, predict if the system is at equilibrium, and if it is not at equilibrium, which way will the reaction shift? So we want to first know, is it at equilibrium with these concentrations? If it's not at equilibrium, are we going to shift right, or are we going to shift left? And here is our reaction right here so that we can write our Q. So we're going to be calculating Q, and we're going to compare it to the K that we already have. So Q is like a test. You're running a test to see if you're at equilibrium, and if you're not at equilibrium, then which way are you going to shift to get to equilibrium? All right, so let's first write Q for this reaction. So I'm doing part A first. Now, my expression for Q is going to be the same for all of these because it's just products over reactants raised to the stoichiometric coefficients. So these are both raised to the first power, and then my reactant is going to be squared. Okay, so you can see, again, I'm writing it the same way I write K, but this is Q because it's a test. We don't know if it's at equilibrium. So I'm going to put in my concentrations here. Now, you'll notice this problem's a little tricky because it gives you moles, but it doesn't give you concentration, which is moles per liter. Now this one, the first part A, is easy because it's in a 1 liter flask. So I'll just do one sample calculation. So let's say I'm trying to calculate my concentration of nitrogen. Well, remember, concentration is just moles over liters, which in the case of nitrogen is 2 moles. 2 moles of nitrogen over liters. We're in a 1 liter flask. So this is just a molarity of 2. So I really don't have to do any calculations. I'm just dividing all of these by 1, which just gives me the same number. It just changes the unit on it. Okay, so I just calculated my concentration of nitrogen, and that is 2 molar. Now my oxygen, again, it's 2.6 moles divided by 1 liter, so that's 2.6 molar. And this is all over my nitrogen monoxide. Here it is. 0.024, and don't forget that is squared. Okay, so when I do this calculation, I get a Q of 9.0 times 10 to the 5th. So this means that Q is greater than K. So if Q is greater than K, then I am going to shift left. Or you can think of it as shifting towards the reactants. Okay, so that is part A, but let's do part B and part C. So I have all our numbers written up here, and we're going to do the same thing. We're just going to be calculating what Q is. So I'm doing part B now. So Q is still the same expression, but remember I need concentrations. So part B, I'm actually going to have to do a little bit of calculation to get those concentrations. Okay, so maybe I'll do this in green. So we'll say my concentration of nitrogen is equal to my moles of nitrogen over my volume, which is a 2-liter flask. And so that is, whoa, okay. Sorry, I looked at the wrong number there. I was very confused. Okay, so that's nitrogen. Let's do the same for oxygen. 2.6 moles over 2 liters. So that these are all in the same size vessel. This is why they're all in 2 liters. So oh no, not 2.6. Sorry, that's 4. I read the wrong number. My bad. Sorry, this should be 4.0. I should underline these as I do them because that's going to help me keep track. I was using the 2.6 up there. All right, so this is a 2 molar solution. And then last, I'll do my nitrogen monoxide. And this is 0.032 moles, again, in a 2-liter solution. And that is 0.016. Again, that's concentration. Okay, so now I can plug in all my numbers into my Q and figure out what's going on here. All right, so Q is equal to nitrogen 0.31, oxygen is 2, and nitrogen monoxide is 0.016. Now don't forget to square that. That's a really easy thing to do, is to forget to square that. Okay, so this gives me a Q of 2.4 times 10 to the third, which, when you know it, is the same as K. So we've got Q is equal to K, so this is at equilibrium. All right, so B is at equilibrium. Let's see if I can squeeze C in here. Again, my Q stays the same, so I'm not going to bother writing it down again because I've already got it there. But I do need to calculate my concentrations. All right, so I've got my concentration of nitrogen. I'm going to make sure I underline it this time, 2.4 moles. And this time we're in a 1.5 liter flask. You could also be in a milliliter flask. So that's something to keep track of. So you might have to convert milliliters to liters and then calculate concentration. So just kind of FYI there. Okay, O2 is 1.7. 1.7 moles over 1.5 liters. That is 1.1. Again, molarity. And my last one is my moles of nitrogen monoxide. Okay, so this is 0.060 moles over 1.5 liters, and that one gives me 0.04. I'm going to squeeze in that capital M there. Okay, so I've got my concentrations. I can plug into my expression for Q and calculate what Q is. So Q is going to equal my nitrogen concentration times my oxygen concentration divided by my nitrogen monoxide squared. So I get a value of Q of 1.1 times 10 to the third. So my Q is smaller than my K. Remember, my K up here is 2.4 times 10 to the third. This means I am going to shift to the right, or I'm going to shift to make more products. Okay, so that is how you use Q. That's how you calculate Q. Now, some of these you could maybe predict. So seeing, well, I don't know if you could predict this one because you do have some product, but not a lot. But maybe you would say, um, yeah, that I'm trying to find one that's totally obvious because I don't think without calculation that you would know what this is. Anyway, sometimes you don't have to calculate Q. You can just look at a problem and know it's going to shift left or right again, especially if you have no product or no reactant, then you know which way it's going to shift. But if you have concentrations for all of your reactants and products, I do recommend calculating Q because then you know for sure if it's at equilibrium or if it's going to shift. Okay. So what we've got now is we've got a real true equilibrium problem. So this one is going to take a little bit of work. I'll just warn you. All right, so the value of K for the following reaction is 0.090, again, at a specific temperature, 25 degrees C. Calculate the equilibrium concentrations for all species if initially you have 1 gram of water, 2 grams of Cl2O, and it's added to a 1 liter flask. Okay, so because we're only specified amounts of our reactants, we can assume that we have 0 products, which makes this a little bit easier because we already know then which way it's going to shift. If we only have reactants, then the equilibrium is going to shift to form products. So it's not going to let products sit there and be 0. The forward reaction is going to run until it hits equilibrium. Okay. The first thing I see, though, is because we have reactions going on, we need to be in concentration. We need to be in molarity. And the first thing we need for molarity is we need to get these grams converted into moles. So let's go ahead and get these grams converted into moles. So I have 1 gram of water. Molar mass of water is 18.0154 per 1 mole of water. And this is 0.0556 moles of water. Now, to get concentration, this is going to be a little bit easier because we're in a 1 liter flask. So to get moles per liter, I'm just going to divide by 1 liter, which gives me the same number, but now we're in molarity. So at least this part of the calculation is easy. Okay, so that's water. Let's do the same thing for our Cl2O. This is 2 grams Cl2O. I guess that's dichlorine oxide. Okay, molar mass here is 86.9054 grams per 1 mole. And this equals 0.0230. This is moles. But to convert to molarity, I only have to divide by 1, which makes my math a lot easier. 0, and now this is molarity. Okay, fantastic. So that's molarity. Let's go ahead and, well, you know, just because it's not going to take that much time, let's calculate Q because I want to show you how you can calculate Q, again, if you're unsure and you're going to get the right answer. Again, we know this is going to shift towards products. It's going to shift right, but what if you plugged in the numbers? So remember, your Q expression is just like your expression for K, products over reactants. Okay, here we go. Bam. So let's put in our concentrations here. And what you're going to see is I have to put in 0 up top, which is allowed. So you can see at this point, it doesn't really matter what my concentrations are of my reactants because this is going to equal 0, right? Okay, so we have Q is less than K, so we're going to shift to the right, or we're going to make products. Okay, so that's how you can prove to yourself that yes, you are going to shift to the right. You're going to make some of your products. But the question is, how much of my products am I going to make? I'm going to give myself another page. I should have done this beforehand. Okay, rewriting my my equation. I have H2O plus ClO2 in equilibrium with HOCl2, sorry, that should be a 2. My expression for K is this guy squared. Oh, sorry. There's no 2 here. I'm not transferring very well, am I? Okay, and this is over water. And so, see, it's Cl2O. I am just, apparently it's too late at night for me. Yeah, Cl2O. I'm not getting my formulas right. Okay, it's too bad I can't drink a coffee while I'm doing the live stream. So here's my expression for K. Here is my my balanced chemical equation. So to figure out what my concentrations are going to be at equilibrium, I need to do an ice table. So yay for ice, right? All right, so what do I have initially? Well, I did calculate these concentrations, right? So I calculated my concentration of water and I calculated my concentration of Cl2O. So let me put those concentrations in. These are initial concentrations, 556. And I'm going to have to kind of squeeze this one over. And I don't have any of my product, so that is 0. Again, we know the reaction is going to shift left, which means for what is consumed or what my change is, I'm going to use up some of my water and some of my Cl2O. I don't know how much. This is why I'm calling it X. And I'm going to make some of my product. Now do notice I call this 2X because there is a 2 right here. So you have to take your stoichiometry into consideration. These are both just minus 1X because there are assumed to be 1s in front of that. Okay, so back to my ice table. To get my equilibrium concentrations, of course, I just add down the column. So my equilibrium concentrations are kind of these gross expressions. And they're all going to be shifted right because I can't. Here, I'll put parentheses around them so you can see what they are. And then, of course, it's just going to be 2X for my product. All right, so I have my equilibrium concentrations. So now I can plug it into my value for K, or my expression for K. So K is equal to my product, which is just 2X squared, over both of these quantities, again, from my ice table. 0.230 minus X. Let me extend that fraction bar a little bit more. And of course, I do have my value for K, 0.09. So we have an expression with one variable. We just have X here. So we can solve for X. Now this is going to be a little bit nasty to solve. We are going to have to use a quadratic equation. So I'm going to try to run through these steps, these mathematical steps, hopefully a little bit quickly because it does take time. But just suffice to say, this is what can make equilibrium calculations hard, is it is very easy to get lost in the math here. So just be really careful with your algebra. Okay, so let's start to simplify. I'm going to simplify my numerator. And I'm going to distribute, or I'm going to FOIL for my denominator. 8 times 10 to the negative third minus 0.0786x plus x squared. Sorry, that is an x. Of course, this still equals 0.090. Okay, so I'm going to take my denominator over to the other side. So this is going to be 4x squared is equal to 0.090. Again, times this whole quadratic. Oops, sorry, my bad. Because what we've got to do is we've got to simplify this and combine like terms to get to our quadratic. Remember, for the quadratic equation to work, we have to set it equal to 0. I'm gonna need another page again. Okay, so this is 4x squared, and when you distribute, not yet. I skipped a step. Sorry. This is a problem with having all of the steps written out, is it's easy to skip down a line when you just want to get through the calculation. 0.0071x plus 0.090x squared. Okay, now I'm going to set equal to 0, although I'm going to keep my x squared positive here. So really, I'll do this properly because I shouldn't be switching sides. 3.91x squared. So I brought that x squared over, combined like terms. That means the sign on this x term is going to change, and also the sign on this constant term is going to change. 5 times 10 to the negative fourth equals 0. Okay, sorry, I need another page. So these calculations do get quite long. All right, so hold on, back to this one. So I've got my quadratic, and I've got it set equal to 0. So at this point, I can use the quadratic equation. Now, I'm not going to run through the calculation for the quadratic equation. This is why I use a programmable calculator, and I have the quadratic equation programmed into my calculator so that all I have to put in is A, B, and C, and my calculator will give me my roots or my values for x. So I am just going to jump straight to x. So we get, of course, we've got a quadratic, we get 2 roots for x. So I get these 2 roots for x. And it's very easy to determine which one you're going to use. You can't have a negative concentration. So when you do the quadratic equation, if you get a negative root, you're always going to discard that negative root. And generally for these problems, you're going to get 1 positive root and 1 negative root, so it's really obvious which root to use. All right, so this is my value for x. So let's go back and let's calculate these equilibrium concentrations. But I need to go back to my rice table and see what these are, right? Okay, so here is my expression for my concentration of water. Here is my expression for Cl2O, and here is my expression for HOCl. So now I'm going to plug x in and calculate what these concentrations actually are. So again, for my water, my expression was 556 minus x. So now I'm just going to plug in what x is, since I know what x is. Minus 0.0046. So my equilibrium concentration is 0.051, and that is molarity. Okay, so the same thing with my Cl2O. This is 0.230 minus x. So just plugging in what my x is for 6. Here's my equilibrium concentration. 0.18. And for my HOCl, it's the same thing. This is 2x, so again, remember, here's my 2x here. That's where that comes from. So this is 2 times my value for x. And this equals 0.0092. Now, when you hit this point and you've calculated your equilibrium concentrations, you probably just want to put your pen or your pencil down and you want to be totally done. But there is a check that you can do to make sure that you have done your calculation correctly, and that is to plug in for K. So when you plug these equilibrium concentrations back in to the expression for K, you should get the value of K that was given to you at the beginning of the problem. So let's plug these in. 0.0092. So this is something to do, especially if you're on a test, if you have a little bit of extra time and you want to make sure that you got a question right. This is a great check for that. So what I get is 0.092, which is not exactly, but again, it's within rounding error. So we're talking about having a little bit of error in that third decimal place. That's perfectly fine. because we are going to, I mean, in all of the, even in the concentrations, we had some rounding going on here. So if you could keep all of those decimal points in your calculator, then you could probably get enough digits so that you could get closer. But this is perfectly fine. It's totally within error. So yes, you have done this calculation correctly, and it's always nice to have that confirmation that yeah, it's correct. Okay, so no questions. I don't know. Maybe everybody got lost in the math there. It is very easy to do. As always, I am happy to cover any topic that you want to see covered. So if you have a request for a topic, again, if you've got a topic or even a specific question, I didn't know how to do this problem. How do I work this kind of problem? Just let me know, and I'm happy to do a live stream on it, and we'll work several problems that are similar to the one that you're struggling with. So I hope you guys have a great rest of your day. Thanks for watching, and I'll see you next week. Bye.